أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Today we'll be talking about adders and subtractors. This topic has been taken from the course outline of Introductory Electronics. Nowadays we are in the part of digital electronics, and adder and subtractors is one of the basic topics of digital electronics. The basic objective from today's lecture is to understand the type of adders, which include half adders and full adders. So we need to understand in detail what is meant by half adder and what is meant by full adder, and we also need to know the subtractor. And at the end of the lecture we will discuss the binary parallel adders. Let's come toward the combinational circuits that we had discussed before. So we had already worked with the combinational circuits in which there was some input which produced the same output. So that particular correspond to a mathematical function, and in that particular every input has a single unique output. So normally in terms of programming terminology, combinational circuits are similar to functional programs that do not contain variables and assignments. So such circuits are comparatively easy to design and analyze. So we already discussed the different number system. In that, the most important was the binary number system that is used in digital electronics. Binary number system has two digits, that is the 0 and 1. Beside binary number system, we already discussed the octal number systems, decimal number system, and hexadecimal number systems. But normally we are playing with the binary number systems in digital electronics, and binary number systems has two digits, that is 0 and 1. 0 is normally used for off position, and 1 is used for switch on position. So we had binary arithmetics, where we had the addition of binary number system and octal number systems, and even decimal and hexadecimal number systems. So in case of binary additions, we can add two binary numbers in one particular one column, and starting from the right. So that is like you add two decimal numbers. So but normally we say that in case of binary number system, if we add 1 and 1, so there is one carry, so it will lead to 1 and 0. I mean the output will be 1 1 0. So if we come toward this addition, that is 1, it will lead to 1. And if we have here the least significant digit, and here we have most significant digit, so if we add up the, so that will lead to the one carry, and that will be added at the end. So this is a simple binary addition where we had discussed in the topic of number system in detail. So what is actually adders? So if we look and come toward the design of an adder for 1-bit number, so that has a simple specification, that is two inputs, that is normally x and y, and there are two output for that is normally considered to be c and s. So if we look toward the two input 0 and 0, that's output will be 0 and 0, and similarly for 0 and 1 the output is 0 and 1. For 1 and 0 output is like this, and similarly for 1 and 1 the output will be cs, that is 1 and 0. So this is the simple optimization of circuit. So we have three steps for that. One is the specification of that particular system, the second is the formulation, and the third is the optimization, or making the circuit. So this is what we call as adders. So this is called as a half adder, why we call as a half adder, because we look toward the table of that and its diagram that combined. Here we have the input, that is x and y, and here is the output, that is s and c. That was something about the half adder. When we come toward the full adder, so that is if we have a combinational circuit that adds 3 input. I mean, in this particular case the inputs are 3. If we come in the previous case, in that case the output were 2, and the input were 2 and the output were also 2. But in this particular case the input is 3 and the output is again 2. So it basically adds 3 inputs bits to generate a sum of bit and a carry bit. So we can generate a truth table and a sum of output, that is C and S, that is mentioned here. If we add up the 0 0 0, that will lead to 0 0. In case of 1, that will lead to 0 and 1. And this is the combination of all this possible input and possible output. A truth table basically depicts, or it display all the possible input and output in this particular situation. So that is the case, the possible input and output are displayed here. So here we have a simple full adders, and the truth table are the possible input and possible output are also mentioned here. We have x, y and z as an input, and c and s as an output for that. And for each of the possible combination, like for 0 0 0, the output is 0 0 0. For x, y, z value having 0 0 1, like this situation, come and look toward it. So the output is 0 and 1. For the input of 0 1 0, we have the output as a 0 and 1. For the input of 0 1 1, the output is like 1 and 0. And for the input of 1 0 0, the output is 0 and 1. For 1 0 1 input, the output is 1 and 0. The same value is repeated for 1 1 0 input. And for the case of input, that both have a path, both have a on situation, that is 1 1 1. The output is also 1 1. So here we have sum, that is normally the summation, and this is the carry that is leading to that value. This is the basic formula for that, and from that we can have a full adder configuration. Full adder, this is like 2 half adders, and that is manipulating the equation. We can get this from just like the combination of x and y plus z. So this, if we simplify the equation, it will be like this. So this is a simple circuit diagram of the full adder, and which is actually equal to the 2 half adders. So here we have the half adder that is enclosed in this rectangle, and in this shape, and this is another half adder. So the combination of this half adder and half adder, that will lead to the full adder. And because in that case we have in this particular case we have x and y as an input, that is both in the half adder situation. But when that is converted into full adder situation, the other input, that is z, that is also included, and we will have x, y, z as a 3 input that will convert the half adder into full adder, and the output is again S and C, that is the simple output. So this is the simple circuit diagram of the full adder. We have bigger adders, and we have steps how to build an adder for n bit numbers. So that is a bit complicated, and that comes to in the a more complicated situation where we have binary parallel adders which can add n bit numbers, and that normally use n full adders in parallel. So the carriers propagates as in addition by hands. So this is the simple case where we can consider that as a type of binary parallel adders, so which is also called as a ripple carry adder. That is the output as a, these are actually the output that is obtained for all this combination of inputs. So adder and subtractor are for the how we can develop the circuit diagram for the adder and subtractor. That is the most important things. I mean, how we can utilize the adder and subtractor in circuits. That gives us particular input. We can utilize that particular input in that, and that could be useful for us in a circuit to get a particular output. This is the simple situation of adders and subtractors. If you look toward the different arrow bars like C for all this C and S values, this is actually the output, and this is actually all the inputs. So from that we can have type of adders or subtractor, which can be done with the help of different digital part of that circuit. So we have binary parallel adders, that is also discussed, and that is the combination of different adders, and that leads to the ripple carry adders. That is important for us. Simple addition is there, and that is actually the method how to reduce the propagation delay of ripple carry adders. That is a bit complicated things. So what we do in this addition, a carry bit is generated when both inputs bits AI and BI are 1. One of the input bit is 1 and a carry bit is exists. So both in that case the carry and the output is values are mentioned. How we can get the overflow or detect the overflow when we add the values? So that could be done with the overflow to look at all the sans bits. This is like simple addition, that is actually the binary addition, and we can get the overflow or the carry term from that, and that we use for the next upcoming values. So overflow could also be maintained, or it could be mentioned in circuits as well. So in that particular situation, the overflow is here is mentioned with the red color, and the input and output are maintained. Inputs are maintained in the form of A and B, which are A0, B0, A1, B1, A2, B2, and A3, B3, and the output are maintained, that is named with the S0, S1, S2, S3, and the single Cout is obtained over here, that is in, and overflow is obtained at the S3, that is at the final value before the output, and from that we can get the overflow. So adder abstractor is actually the circuit is used to perform the arithmetic operation, that is actually called as the binary addition or subtraction. So therefore we have both adder and subtractors, so that actually perform the arithmetic operation, and it is basically constructed using combinational combinatorial logics. So adders are the most commonly used that do the addition. So we have basically two type of adders that already discussed in the earlier slides, that is the half adders and the full adders. In case of half adders, the most basic, that is actually the most basic of the adders. If the input to 1 bit values x and y, and the output then their output 2 bit sum is a bit carry and sum, so that is actually a half adder in case of half adder. So what is this is a simple this is a simple half adder, we have input as x and y and the output is c and s. We can generate the truth table for that, and that is a simple addition. That is actually not a simple addition actually, but that is actually the binary addition, and from that binary addition we can get the value of that particular case in the truth table. Full adders is actually used to add numbers that are more than one bit wide. So it has three inputs, the two data inputs and a carry input. So the carry input is normally represented by Cin. So the output is the same as the half adder. So it means the output is 2, that is C and S, while the input is 3 in case of full adder, while in case of half adder, that is 2. This is the simple diagram and the truth table for the full adders. We have the input as a x, y and c in, and this is the output, that is c and s. If we come toward the truth table, we have x and y and c in as inputs values, and these are actually the input value that are mentioned here, and these are the output values, that is c and s. Its values are mentioned here. So this is the truth table for the full adder. So the truth table basically describes all the possible inputs and output that are could be used or that could be played with the help of full adder as well as with the help of half adder. So we have a separate truth table for the half adder and separate truth table for the full adders. So as we discussed already, that we have ripple adders as well, and in case of ripple adders, the full adders cascaded to produce an n-bit adders by connecting output C of an adder to C of Cn to the next adder. So the reason it's called as a ripple adder is carry bit ripple through the adder, because it's why it's called as a ripple adder, because the carry could be obtained through the ripple adder. So each full adder has a small propagation delay, and that particular that adds up as the carry bit are propagated or ripple from right to left. So we have one solution to the delay problem, that is the carry look ahead adders. So this adders breaks the implementation of the carry into two parts, that is the generate part, that is could be represented by G, and there is the other part that is called as propagate, and the propagate part is represented by P. So if we basically describe the basic concept behind the the adders, then full adders are a logic component that directly subtract two values. So it has three inputs, that is two data input and a barrow input, and two complement can also be used to implement subtraction. So two complement of a values is the negative of that value, so it is generated by complementing the value and adding 1 in that particular situation. So after discussing adder and subtractor, we come toward the memory. In case of adder and subtractor, as that we have full and half adder that only distinguish from each other by their input and output values. We had same output in both full and half adders, while the input in half adder is 2 and the output in full adder, the input in case of a full adder is 3. So that was a simple difference between that. So coming toward the memory, that is important topic that is related to that. So memory is a group of circuit used to store the data, and that is not actually combinatorial in design, but that could be used as a combinatorial component in the digital circuit, and that could also be used to store the data. So a memory component has some number of memory locations, and in that particular case each of which stores a binary value, that is actually working on the binary number system, and that has a particular argfix length. So the number of location and size of each location vary from chip to chip, that is actually called as a memory chip, but are fixed with an individual chip. So the size of the chip is denoted as the number of locations times the number of bits in each location. So a memory chip of size 512 multiplied by 8 has 512 memory positions. So if we had a memory chip with a 2n location that require adder inputs, so what we can do, the data pins on a memory chip are used to access the data for that particular case. So we had basically two type of memories that normally we use in computer as well. One is called as read only memory, that is called as ROM, and the other is called as RAM, that is called as random access memory. So both of the memories are used in computer. The RAM is basically the storing the data. As soon as the computer switch off, the data from the RAM is removed, and that is vanished, while the ROM, that is the read only memory, that is stored particularly, and that could be accessed in any time when you want to need it. So we have basically ROM and RAM for that, and that has its own individual objective and specification, and its operational method, how it can get the data, how we can retrieve the data out from that, and how that could be used. So normally the personal computer use ROM to store the instructions, and that constitute their BIOS, that is the basic input and output systems for that, and for this purpose the ROM is used, and that completely store or save the data, and BIOS is used, that is the basic input and output systems. And when power is removed from a ROM chip, it still maintain the data. So that is why ROM is non-volatile. I mean, if you switch off the circuit, if you switch off the cell phone, if you switch off the laptop, if you switch off the PC, the data that is stored in ROM could not be vanished, or that could not be erased, but that is maintained even if you want to access the laptop, the computer, or the PC again after some time. Your data is stored, or that is saved, so you can access it. Well, in case of RAM, that is actually the read-only memory, that is the random access memory, is different from ROM because it initially contains no data, so data can flow in or out of the chip as opposed to ROM, which are output only. So RAM loses data once power is removed, so it is a volatile. So if you switch off the computer, the laptop, the tab, or some other electronic circuitry which stores the data, or personal computer, so when you switch off that, the data from the RAM is erased because it is volatile, while the data in the ROM is stored because it is non-volatile. So that is the difference between RAM and ROM, And the RAM is basically used for calculation of operational data. As soon as the system is switch on, it stores the data and we can utilize the data. So this is something about RAM and ROM, and the some description of that, and that is very closely related to the number that for particular adder and subtractor, because the binary addition could be done at that data that is stored in any particular system, that is done with the help of the binary number systems. And for that binary number system, we use some digital circuit for that. Adder and subtractors are basically the basic building blocks, or the type of basic part of the circuit that is used for that particular configuration, where we can add or subtract the data and you can utilize that. So basically what we studied from the whole lecture, we understood that if we are coming toward the input value, so in case of adders, we have two input values. That is in case of this separately is a half adder, and this separate is a half adder. When both are added and this is added with it, it will gives us a full adder. So in this case we have two input values, and we have two input values in the half adder, and the same values are increased to three output input values when we have a full adders. So basically full adder has three input values, while half adders has two input values. So that is used for that particular configuration. So this is actually the combination, and that lead to that. And the truth table is basically describes the combination of all possible input and output values. This is the actually the truth table for the half adder, and that stores the data, or that gives us the inputs, and that when we provide the input in the form of x and y, the output is provided to us in the form of 0 and 1. So this is the combination of that, and this is the simple arithmetic that is actually called as a binary arithmetic that is used for that, and that arithmetic is very important for us when we add. This is the ripple carry factor that is very much important, and this ripple carry factor basically describes when we have multi inputs and multi outputs, or maybe a single output, and both the full adders are working in the type of full adders are working in parallel to each other. So that will lead to the ripple carry factors. So in that carry factors, we can have multi full adders that are working together, and that form the complicated circuit that is used for the data manipulation. So this is again the simple thing where adder and subtractors are used, and that could be simply maintained in the form of circuit diagrams. This is again the ripple factor that is depicted here. So how we can add up the values, that is actually the binary arithmetics, that is the addition and subtraction. Overflow is also the part of that, where we can maintain the output. When we have more or bigger values, we can store or we can stop some of the values out of that. That is actually the overflow, to allow only limited values to the output. That is called as a full C output for that, and that is used basically in the combinational circuit. that is used both in adder and subtractor. So this is something about adder and subtractor that is most important to us for the understanding of memory and the storing of data in digital electronics. So thank you very much for today's lecture.